Okay, in this video we're going to be looking at a thing called enthalpy of formation, and we're going to be looking at how enthalpy of formation can be used to determine the enthalpy of a reaction, whether that be a combustion reaction or anything else. Basically what the enthalpy of formation is, it's the amount of energy change when a particular substance is made from its elements. So for example, if I was to take C8H18, so octanol, which is a liquid, which you found in most petrols, then I can see that the two elements in this are carbon and hydrogen. So I'd have 8 carbons, which is a solid at room temperature, and there's 18 hydrogen atoms, so that's 9 hydrogen molecules, because we have to do it as an element, not as an atom. Likewise, we could have, say, water. So water is normally room temperature, liquid at room temperature. It's made from hydrogen, which is a gas at room temperature, and oxygen, which is a gas at room temperature. Now here we see that this isn't balanced. The unit for enthalpy of formation is kilojoules per mole, so I'm not allowed to change this at all. It's got to stay as 1 mole in this equation. So instead I accept that these are moles, not molecules. So I'm not saying 1 molecule of hydrogen reacts with half a molecule of oxygen to make 1 molecule of this. So 1 mole of this is going to react with half a molecule of this to make 1 mole of this. Half a mole of this makes 1 mole of this. So then I get my kilojoules per mole, how much energy is released when water is made. And the reason that we use these is that we can use them in 2 different ways. One is to find enthalpy of reaction when we're just given enthalpies of formation, and that's given a nice little thing here where the enthalpy of reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpy of formations of the reactants, which sort of makes sense. You're going to unmake these, so that would be the opposite to them being made. That's why it's a negative sign. And you're making these, so again that makes sense. Now with these enthalpies of formation, only molecules and compounds have got these. Elements do not. And the other way that we're going to use it, and hopefully I'll be able to show you in the time we've got here, is in a thing called Hess's law. Now the thing that's great about Hess's law is that you don't need to have enthalpies of formation. Any enthalpies you've got can be combined to find the enthalpy of a reaction. So that's quite useful. Okay, so the first one we're going to do is look at using the first way, see if we get the same answer when we do it the second way, for the complete combustion of octanol, which is the one we've got here. Sorry, not octanol, octane, which we've got here. Okay, so octane, complete combustion. The balanced equation for this is given as being 2 octane molecules react with 25 oxygen moles of oxygen to make 16 moles of carbon dioxide and 18 moles of H2O. And I'm going to have it as liquid there, even though we know in combustion you'd normally make steam. We're going to leave it at standard conditions. In a question like this, where we're asked to find the enthalpy of combustion, which is just an example of enthalpy of reaction, we have been given the following information. We've been given the enthalpy of formation of octane, and that is negative 250 kilojoules per mole. We have been given the enthalpy of formation of carbon dioxide, which is negative 394, and the enthalpy of formation of H2O in its liquid state, which is negative 286 kilojoules per mole. Now you'll notice we haven't been given any value for these 25 oxygens. That's because they're already an element, so they don't get included in these. You can't have an enthalpy of formation for an element. It's already been formed. Okay, so how do we do this? Well, going by that equation we had before, we need to find the sum of the enthalpies of formation. the sum of the enthalpies of formation of the products, which is going to be 16 carbon dioxide, 16 times negative 394, plus 18 times negative 286. Right, so I'll very quickly do that on my calculator. Hope you can see the numbers when I do this. That doesn't seem right. Okay, no it is. Okay, so that equals negative 11,452 kilojoules. Then I need to find the sum of the enthalpies of formation of the reactants. And there's 2 of these, so I can automatically go, oh, that's negative 500 kilojoules. So now I just have to go this number minus this number, and I'll have my answer. So negative 11,452 minus negative 500, so that's the same as adding, so plus 500, and I get my answer of negative 10,952 kilojoules. Now I'm not putting kilojoules per mole because in the equation I've got 2 moles there. So technically speaking, the right answer is kilojoules because nothing in there is 1 mole. So that would be wrong to write kilojoules per mole. So that's the first way to do it, using enthalpies of formation. The second way is using a thing called Hess's law. And in Hess's law, we're going to try and use those other equations to try and find the enthalpy of the reaction. So again, I'm going to do my desired reaction, or the one I'm trying to find out. Now, I'm sorry, I'm going to leave out states of matter this time, just for speed. Alright, now the enthalpies of formation I've given, I'm going to write the equations out for those. So the first one we had was the enthalpy of formation for this is negative 250. And again, I'm sorry, I'm just going to leave out the units just for now because it's my working. There's 8 carbons and 18 hydrogen atoms, so 9 H2 molecules. I'm given the one for carbon dioxide is negative 394, so that's made from 1 carbon and 1 oxygen. I'm given H2O, which is negative 286, so that's 1 mole of hydrogen, half a mole of oxygen. Okay, so what I'm going to do here is have a look at basically what I'm trying to get, which is the octanol and the oxygens to be reactants, and the carbon dioxide and the water to be products. Now I can see here carbon dioxide and water are already products. So what I'm going to do is I'm actually going to use the fact that those equations are already there to try to construct this top equation. So if I have a look at carbon first, there is 1 carbon dioxide here, but I want there to be 16. So I'm going to write out my carbon equation 16 times. So 16 carbons plus 16 oxygens going to 16 carbon dioxides. Now the enthalpy for that will be 16 times negative 394, which is negative 6304 kilojoules. Then I'm going to do the same thing with the water. There are 18 of these, so I need 18 of this equation. So I'm going to have 18H2 plus half times 18 is 9, so 9O2 goes to 18H2O. So that's going to be 18 times negative 286. And you can see already that we're getting the same sort of numbers as before when we did it the other way. Alright. Then I have a look at this equation here. Well, actually, this has got octane on the wrong side. So I want it to be on this side, not on this side. Therefore, I'm going to flip the equation. Now, if I'm going to reverse the equation, I have to reverse the enthalpy as well. So no longer will it be negative 250, it will be positive. I'll show you what I mean. C8H18, when I unmake it, as it were, will be 8 carbons and 9 H2s, which would give me positive 250. But actually, if I look at my original equation, it's got 2 of those, so I need to double it. So 2 of those, 16 of those, 18 of those, and rather than 250, it'll be 500 kilojoules. Sorry, that's a bit messy there. Probably should have used a pencil. Okay, now, if anything appears on the reactant side and the product side, I can cancel it out. So I can see there's 16 carbons here, and there's 16 carbons here, so they are gone. There are 18 hydrogens here and 18 hydrogens here, so they are gone. What I see now is I've got 2 C8H18s. Yes, that's what I've got there. I've got 16 plus 9, 25 oxygens. Yes, that's what I have there. I have 16 carbon dioxides. Yes, that's what I have there. And 18 waters. Yes, I have that. So if I was to add these enthalpies up, I should get the value for this enthalpy, the value for enthalpy of combustion. And again, you'll see it's exactly the same as before for the calculations, just the method that got us there was different. And we end up with negative 10,952 kilojoules, same answer as last time. Now, this seems more complicated, and it is, but the reason that it's worth knowing this process is sometimes you're not given just enthalpies of formation. You might be given enthalpies of combustion and formation in combination. The only way that really you can do that is to use the Hess's law method. The previous method using the sum of the enthalpies of formation won't work for that method, hence showing you both. I hope that's some help. And just a piece of advice, if you just learn one method, learn the Hess's law method, because it works for both.